Okay, so picking up where we left off, we're continuing our discussion of hyperbolic functions. And what we're kind of doing here is we're using what we know about the circular trig functions as a guide for how to study the hyperbolic trig functions. So far what we've done is we've defined the hyperbolic trig functions, and we have looked at some identities, and we have looked at their derivatives. So that's kind of what we've already done with the circular trig functions as well. But kind of continuing on in that vein, in trigonometry you learn that all of your trigonometric functions, in particular sine, cosine, and tangent are the ones you do this the most with, they have inverse functions. We have an inverse sine, inverse cosine, inverse tangent, and so on. We would like to see if we can do the same thing with the hyperbolic functions. So for example, if we wanted to find y equals inverse sinh of x, then by the definition of inverses, this is equivalent to saying that sinh of y is equal to x, right? So if I took sinh of both sides of this, it would cancel the inverse sinh and so on. Similar for Cosh and Tange. Now, excuse me, in order to do that, if you remember when we talked about inverses in this class and when you would have talked about it in algebra, there's a condition that needs to be in place for a function to have an inverse. It needs to be 1 to 1. And if you have the graph of a function to look at, that's a simple matter of determining whether or not it passes the horizontal line test. So going back to the graph of sinh, cosh, and tange, I can see that both sinh and tange would definitely pass the horizontal line test, but cosh would not. So cosh is going to require a domain restriction. In order to get a definition for the inverse cosh function, we first have to take cosh and restrict its domain to all of the non-negative real numbers. Cosh, we're going to set x to be greater than or equal to 0. That would give me the right branch of the cosh function, which I can see by itself does pass the horizontal line test. Okay, that x becomes a y when we flip things around here. So that's where you're seeing this y greater than 0 here. This is accounting for that restriction that we had to put on the cosh function to make sure that this is 1 to 1. But once we've done that, all three of these things will have inverses. And the inverses, as we know from our discussion on inverse functions, will have graphs that look like reflections of the graphs of sinh, cosh, and tange respectively across the line y equals x. So you can compare these to the graphs that I just showed. Notice the cosh is including the restriction that we talked about. And that's what these graphs would look like. The domain and range of each one is also indicated down here. Now, the way that we're defining these up here is not terribly useful, because I know how to find, for example, sinh of 1. I know how to plug a 1 into the sinh function because I've given a definition of the sinh function involving exponentials, and I know how to plug a 1 into an exponential. So that's fine, but the way that I'm looking at the inverse functions here, I don't know what to do if I have to plug something into this. So this way of thinking about the inverse hyperbolic functions is not really practical. We need a different representation for them to be able to use them in practice. And down here we have representations of them. So it turns out that the inverse sinh function is equal to the natural log of x plus the square root of x squared plus 1, and this is defined for all real numbers. Inverse cosh is defined or is equal to the natural log of x plus the square root of x squared minus 1, and this one is only defined for x greater than or equal to 1. This actually is a direct consequence of the domain restriction that we put on the cosh function to get the inverse cosh function. Notice from the graph you can see the domain would be all numbers greater than or equal to 1, but even in this definition we could see why if x is going to be positive, it has to be greater than or equal to 1. And that's because if it's less than 1, then this thing in here, let's say that x is equal to 0, for example, I'd have the square root of a negative, right? Now you might say that x could be less than negative 1, because then squaring that will give me something greater than 1, so this wouldn't be 0 anymore. But x plus that, if this x is negative as well, is going to give me a negative number on the inside of the parentheses here, and the natural log is not defined for negative numbers. So this domain restriction makes sense with what we're seeing here. Then finally, here's a definition for inverse Tange. Now, you don't need to take these for granted. We can derive these, right? And it kind of makes sense that if the sinh, cosh, and Tange functions involve the exponential function e to the x, it sort of makes sense that we would expect the inverse of the exponential function to make an appearance here as well, which is the natural log function. But it's not immediately obvious why these look exactly the way they do. So we're going to derive one of them to give you a sense of how you could derive the others as well. What we want to do is show that the inverse Cosh function, inverse Cosh of x, is equal to what we saw it equal to in the previous page. Natural log of x plus the square root of x squared minus 1. So this takes a little bit of algebraic trickery, but what we're going to do is start with the way the inverse Cosh function is technically defined. If I set y equal to the inverse Cosh of x, then by definition this means that x is equal to Cosh of y. Now I'm going to use implicit differentiation. This is similar to what we did when we found derivative of our inverse trig functions back in whatever section that was. I'm forgetting what section that was. I'm sorry, I'm doing the wrong thing here. I was thinking that I was taking a derivative. I don't want to take a derivative, but I do want to do this step. So now that I defined x to be equal to Cosh of y, let's use the definition of Cosh. That's e to the y plus e to the negative y over 2. Okay? Now what I'm going to do is try to create something that looks a kind of like a quadratic, and I'm going to end up using the quadratic formula. So what I'm going to do is take this and multiply both sides by 2, so that this side becomes 2x. And this side is now e to the y plus e to the negative y. Okay? Now I'm going to subtract the 2x over, so that I get e to the y minus 2x plus e to the negative y. Then what I'm going to do is multiply both sides of this by e to the y. The goal is to get this y to cancel that negative y right there. 0 times anything is 0. E to the y times e to the y would be e to the y squared minus 2x e to the y plus e to the negative y times e to the positive y is just 1. Those are reciprocals of each other. Okay, and what we have here is a quadratic in disguise. If I think of e to the y, that entire thing is my variable, then I have a term where my variable is being squared, a term where my variable is being multiplied by what I'm going to interpret as a constant, even though it's not, 2x, plus 1. So this is taking the form of a quadratic, and if I put a 1 here, I can think of that 1 as a, I can think of this negative 2x here as b, and I can think of this one as c. I can use those in the quadratic formula because this is set equal to 0. So this implies that my variable e to the y is equal to negative b, which would be positive 2x, plus or minus the square root of b squared, so that's negative 2x squared, which is 4x squared, minus 4ac, 4 times 1 times 1, that's 4, all over 2a. 2a is 2 times 1, so it's still 2. Okay, I can factor a 4 out of here, and then the square root of 4 is 2, so that comes out as a 2. 2x plus or minus 2 times the square root of x squared minus 1, all over 2. Notice I can cancel these 2's now, and I get x plus or minus the square root of x squared minus 1. Now I do need to be careful here because even though I have a plus or minus, the minus actually doesn't make any sense. And the reason for that, excuse me, the reason for that is because this thing will not be defined if I'm using subtraction. So to be a little bit more careful about that, remember how we defined x to be greater than or equal to 1? If x is greater than or equal to 1, then x squared is going to be greater than or equal to 1 minus 1. This is going to give me something that is, oh, you know what, I'm using the wrong justification here. Regardless, if we use minus, this thing ends up being not defined. I need the plus. So that leaves me with e to the y equals x plus the square root of x squared minus 1. To solve for y, I take a natural log of both sides, so that y is equal to the natural log of x plus the square root of x squared minus 1. Okay? So again, I kind of botched my explanation for why this minus is appearing here. Basically, this is because we want come back to my graph here. There we go. We want this branch of our Cosh function after being reflected across the line y equals x to be appearing here. Notice if instead of, if I go back to my original Cosh function, if I, instead of restricting my domain to this positive branch of the Cosh function, if I restricted it to the negative branch, then the graph of the inverse Cosh function would have given me a branch down here instead of up here. And that branch is what would correspond to having a minus here instead of a plus. So to make it match with how we restricted our domain, we want a plus instead of a minus there. That justification is not super important. If you get really confused by that, don't worry. It's the important thing is that you know that this is what the inverse Cosh function is equal to. Okay? So now that we've done that, the next step would be to talk about the derivatives of our inverse hyperbolic functions. And we actually don't need to use this form of the inverse trig, the inverse hyperbolic functions to come up with these. But take a look at these and compare them to the derivatives for the inverse trig functions that we've defined earlier. They should look very, very similar with a few subtle differences. Okay? I want to derive one of them, though. So let's go ahead and do this one. How do we show that the derivative of the inverse Tange function of x is equal to 1 over 1 minus x squared? So this is similar to what we did in the previous example, where we're going to go to the definition. I'm going to say inverse Tange of x, let's set that equal to y, so that I can write Tange of y equals x. Now I want to differentiate both sides with respect to x. In the Tange function, we've got a derivative for that already. So that's work that we did previously. For reference, I'm going to go back to that page really quick. Right here. Remember, it's very similar to what we see in the inverse, or in the circular trig function. So its derivative is sech squared. Okay? So differentiating both sides of this, I'm going to get sech squared of y, but because it's implicit differentiation, I'm also going to get a y prime that comes out of that. On the right-hand side, differentiating x with respect to x is going to give me a 1. So this means that y prime, after dividing both sides, y prime is equal to 1 over sech squared of y. Now at this step, it's going to be useful to think about the trig, the hyperbolic identities that we have talked about. So returning to that for a second, one of the identities that we got was this: sech squared of x is equal to 1 minus Tange squared of x. So if I were to use that here, I have y's instead of x's, but that means that I could write 1 over, what did I say it was? It was 1 minus Tange squared. Yeah, 1 minus Tange squared of y. Okay? However, Tange of y is equal to x. So I can replace this Tange of y with an x, making an x squared here. And that gives me y prime equals 1 over 1 minus x squared, which is exactly what we were expecting to see. Okay? So there's my derivation for that. All right, we're going to wrap things up with one last example of finding a derivative. This time we want to evaluate the derivative of inverse tangent of x cubed. So this is going to require the chain rule. And up here, we evaluated the derivative of the inverse tangent function. So for this, of x cubed, I want to take the derivative of the outside function, which is 1 over 1 minus normally x squared, but I evaluate it at the inside function, so that would be x cubed squared, times the derivative of the inside function, 3x squared. This simplifies to 3x squared over 1 minus x to the 6th. That was a super fast, super easy one. It's just using the chain rule, and now that we know, I forgot to put my h there, now that we know the derivative of inverse tangent, we could just go straight to that derivative. Okay, that's going to wrap things up for chapter 3.